previous sessions, we have seen to design a system using schematic entry in ISC Project Navigator. So let's close the project and start up with the full adder using Verilog entry. So the module will be looking something of this kind with the terminals as shown. So let's get started. So for this, we'll create a new project as project 4. Having done that, we'll add a new source as Verilog module and we'll name it as full adder. So one can add the port name here and with the directions as input, outputs or in-out. But we'll start it from the scratch. So to start up, we'll have the module definition and here the module name is full adder. So this is the module name which is already there. Now let's add the terminals. So we'll add the terminals or the ports as A, B, C, then sum and carry as the output. Then appropriately we'll mention the input and output declarations as single bit. All variables here are treated as a single bit variable, like single bit port. So the module and the terminals are declared. Now to define the functionality, we'll be using here combinational idea, or we'll be using assign block. So sum as XOR of 3 inputs. So here we have apostrophe sign and similarly with the carry output. As A and B or B and C or C and A. So here we go. So this is very simple way of designing a system with the Verilog entry. So let's quickly try synthesizing the module so that we can view the register transfer logic. We can view the register transfer logic as a schematic. So having synthesized successfully, we get this check mark. Then one can select the top level block, which looks similar to the part what we started with. And the internal functionality, it is governed by the way in which we define the module. So module is created. So let's test the module. So we'll be creating a test fixture and we'll name it as test FA. So if things are fine, we'll be getting the input and output declared in the test fixture. And as we have already taken up in the previous sessions, we'll be defining appropriate input variance. And then we can add $finish command. So let's quickly change the input possibilities. So let's shift to the simulation mode and select the test fixture. Having done the check syntax, let's simulate the model. So we get the output in the ISIM program. So let's shift the output of sum and carry as shown. And one can use the directional or navigational key in the keyboard to check the outputs. So here we can check the functionality of a full adder with 3 inputs, A, B and C, and sum and carry as the output. So this was one way of defining a module, wherein we have used the first way of defining the module is called as structural description, wherein we were using or we were preserving the structures by AND, OR and XOR gates. And this way, the second way, is what we call as behavioral description, wherein we are defining the system behavior. Let's try the as addition, higher level. So now let's try to use the idea of hardware description. So here we can use some higher concepts of array concatenations. So here we'll be defining CY and sum, which is a 2-bit number, and then here we'll be using plus operation, or here we'll be using addition operation. So this 3-bit will add to give 2 bits, where LSB will be sum and MSB will be going to the carry. So let's synthesize. In fact, the first way of declaring the module was structural type of declaration or defining a module. The first way was structural description, and the second way is the behavioral description. So here we can see the internal functionality, which seems little different from the structural way what we had. Since the system is same, so let's quickly test the module. So here again, we can see the input and the output variances. So one can again quickly verify the functionality.